Okay, so section 5.4, the fundamental theorem of calculus. Okay, this is theorem number 4. We're gonna learn, we are gonna learn 5 theorems. We already learned 3. First semester we had the IVT, the intermediate value theorem, the MVT, which is the mean value theorem, and then the EVT, which is the extreme value theorem. So that's 3 already done first semester. Second semester, we're going to do 2. One is the fundamental theorem of calculus. It has 2 parts. And then I think 2 sections later. Oh, next section, we're going to learn the mean value theorem again, but for integral. Okay, so today we're doing fundamental theorem of calculus. There are 2 parts. So I'm just going to give you what the theorem says for now, and then we're going to do one by one, and we're going to take 3 days on it because we really need to understand this very thoroughly. Okay, let's say that f is continuous on a and b. Okay, so that's the part that it has to happen. It has to be continuous. You cannot have asymptotes. If g of x is from integral from a to x, a is just a number, x is a variable, f of t dt, then g prime of x is equal to f of x. Okay, that's the first part of the FTC, or fundamental theorem of calculus. Second part. The integral from a to b of f of x dx is equal to big F. Big F means the integral function. Okay, big F of b minus big F of a, where f is any antiderivative of f. That is, f prime is going to equal little f. Okay, so the second part of the theorem says the integral from a to b of little f of x is equal to big F of b minus big F of a, meaning the integral from b minus the integral of a. And the definition of big F and the little f is shown below. All right, so last night you watched a video on accumulation function. Basically, what fundamental theorem of calculus does is it ties in derivative and integral. So before this, they had no idea that they were related. And then after, I think it was Newton, he was doing some mathematics and he found out that integral and derivatives are actually related to each other. One is basically the inverse of, or not the inverse, the direction-wise of each other. So let's look at FTC first part, which is the accumulation function. And we're going to spend a lot more time on this in the next chapter. So accumulation function says if you have this this graph, let's say this graph looks like this. This is f of t. And let's say that you want to figure out the area between A to B. If you want to figure out the area between A to B, you just need to find the integral from A to B of f of t dt. Right, so basically this integral sign means I want the area between A and B of the area that's underneath the curve f of t. So looking at this graph, this is f of t, so this area is what I want. Right? Make sense? that's what we've been doing for a week and a half. Okay, so this is the area. Now, let's say that B is not fixed. B is not just a point on the graph. B is actually moving. Okay, so then X. Basically, X can move. We don't really know where X is, but it's going to be somewhere on this curve. So then when you find the area underneath this curve, it's from A to X of f of t dt. We're still looking at the area underneath the curve, but this time it's going to be from A to X. The only difference is that because X is moving, we are not really going to have a set number because we are not going to have a number until X is set. Does that make sense? Right? So then this is going to give us the area between A to X, which is going to be a function, a new function, G. Does that make sense? So the area underneath the curve is actually another function based on where we are on the curve. Yes? Okay. All right, so let's just use that fact for now. Basically, what I'm saying is the area underneath the curve can become another function based on where the x value is. Okay. All right, so let's look at this question. The graph of the function is given below. So it kind of looks like that. You have two straight, or actually three straight lines. 1, 2, 3, and then you have this curvy thing in the middle. All right, we are going to look at this. G of x is equal to the integral from 0 to x of f of t dt. And then they tell you that this curve is f of t. So g of x is equal to, integral means what?
Area under the curve.
Area under the curve. So g of x is equal to area underneath the curve f of t from 0 to whatever x is. Okay, so basically g starts from here and then it's accumulating all the area underneath the curve. All right, so let's look at all of these functions of g and then evaluate them. So g of 0. G of 0 means x is what? G of 0 means x is 0. Okay, so this is basically just plug it into that equation. So this is g of 0, which is from integral from 0 to 0 of f of t dt. All right, so let's look at the curve. What is the area underneath the curve from 0 to 0? Nothing. So this is 0. All right, g of 1. G of 1 means x is what? 1. Okay, so this is the area underneath the curve between 0 and 1 of f of t dt. So try not to get t and x confused. Okay, so 0 to 1. From 0 to 1 underneath the curve. So what is the area there? Area underneath the curve between 0 and 1. 1. All right, you guys know what to do? So basically, g of something is just saying where that location of x is, and then they defined g of x such that it is the area between 0 and whatever you end up on the x. Okay, so let's have you try the rest. G of 2, G of 3, G of 4, and G of 5. And I'll make this a little bigger. So basically go from 0 to 5 on the x values. Okay, so let's take a look. G of 2, let's see, Chen, what'd you get? 3. G of 3, Jessica, what'd you get?
3.5.
3.5, okay, that sounds good. Rachel, G of 4.
I didn't do it yet.
You didn't do it yet? Kevin, what'd you get? 3. And then Yvonne, last one, G of 5. 2.5. I think it's 2 exact. Because this area and this area just cancels out, and then everything else is just exact numbers. All right, okay, so that is kind of how you use accumulation function. So basically saying integral is really just a function of area, and that function has a variable in itself. Okay, so that is like the first part of the first part of accumulation function. Okay, let's look at the actual FTC. Now the second part, so if you look at FTC part 1, it says g of x is equal to the integral from a to b or a to x of f of t dt. The second part says, therefore, g prime of x is equal to f of x. All right, this is the part that is a little confusing. So the derivative of that function, remember that function was like this. The derivative of the function is just the function itself. The derivative of g is just f of x. N? X, sorry. So this part took me a long time when I was learning it to understand why this is the way it is. But it's actually not that hard to understand. So let's kind of look at this curve again. This is f of t. Okay, well, let's talk about what derivative is. Do you guys still remember the definition of derivative? Slope. And then what's the formula for that slope using like the limit as h goes to 0 of that whole thing? Do you remember? No. Okay, so it's g of, so basically it's the a rock, right? G of x plus h minus g of x over h. So f of b minus f of a over b minus a. And where does that h come from? So let's say that this is somewhere on this line. This is x. This is x plus h. So you're just a little bit farther away. So x plus h. Derivative by the definition of derivative is f of b minus f of a over b minus a. So basically g of x plus h minus g of x over h. Now let's see what happens. G of x plus h. What is g of x plus h on this graph? What is g of x actually? Is it the curve? Is it the area underneath the curve? Or is it like the slope of the curve? What is it? G of x.
Oh, it's the slope underneath the curve.
Ooh.
In the box.
Oh, not the point. The point itself here is f, right? This is the curve f. So where is g? How everybody's confused. Huh? Not the height.
Is it area?
Yes. Remember, g is the derivative of f. So g is the area underneath this curve. Okay? So g of x plus h is this area. Right?
Wait, so g of x is the entire area under the curve?
Yes, up to x.
Up to x.
From 0 to x?
The number doesn't really matter. From where, it doesn't really matter. But let's just say from 0 to x. Okay, so g of x plus h is this part. Okay, and then g of x is this part. Yes? Basically from whatever to x. From whatever to x plus h. So g of x plus h minus g of x is just this leftover part. Make sense? Big area minus this area is this part left. Yes? So basically, this question or this derivative just becomes the leftover area divided by h. Now what happens is we're going to make this h very small, meaning like we're going to make the rectangle very, very thin. So then this area becomes h times this height. And this height is f of x. Yes? Okay, just think that this is a very, 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 very narrow strip. So then f of x and f of x plus h doesn't really matter because they're very close. Okay, so this becomes base times height. And then we still have that h underneath, right? And then so what happens is we are going to let the limit as h goes to 0 of this whole thing. So then that h cancels. That h cancels, and then we just have f of x. So therefore, g prime of x is equal to f of x. The derivative of this area function is that curve itself in terms of x. All right, so that is the second part of FTC, part 1. We are going to now use it. All right, find the derivative of this function, g. So whenever I see this question, I still get kind of scared, like, what? How do I find a derivative of an integral? This is where you have to remember FTC. The derivative of this function is just the function itself. Okay, so FTC says derivative of this function is just f of x. Okay, this part is g of x. This part is f of t. Okay, notice that we are switching variables. The curve underneath the integral is f of t. But we are trying to write a area underneath the curve based on x, and then we're taking derivative, so it is of x, not t anymore. All right. So the question is, what is f of t? It's just this part, right? Right, the f of t is just the function, the curve we're looking at, and g of x is the area underneath. When we take derivative, it is just square root 1 plus x squared. We're just exchanging the variables. Okay, derivative of this integral is just the function itself, but you switch the variable. Okay, but there are some addendums. First, this lower limit has to be a number. That way, when you take the derivative, it's gone because it's just a constant. The top part has to be a variable, and that variable is just one variable. It cannot be x squared, it cannot be x cubed, it cannot be anything but just x or just t or whatever that variable is. Okay, so it has to be a linear, I guess, not linear, it just has to be x. Okay, so anything else besides this form, we're going to talk about next time on how to solve those kind of problems. Okay, so let's have you try one. Find the derivative of this function. Sorry, dt. Okay, so the question is, what is h prime of x? Okay, this obviously this is a very simple question, but what I want you to start doing from now on is look at the limit of this integral. Is it in the right form so I can just substitute? So the question is the lower limit just a number? Yes. Is the top limit just an x or a t or something like that? Yes. Then just substitute. Okay, so this answer is just sine x over 1 plus x squared.
What about the 1 to x?
The 1 to x, when you take the derivative, the whole thing just switches. Because based on what we proved before, the derivative is just the function itself.
Okay, but it's 1 to x, not 0 to x.
Yes, because the one part, if you kind of think about it, you could do a very simple derivative, integral. Let's say you do 2x, 1 to x, t. Okay, let's just, because this one is doable, we can just, do this. So h of x is equal to t squared, right? Yes. No? Yes? No. Okay, let's do an even easier one. Let's do, sorry, I can't erase on this. Let's do 1 to x of 2. Okay, flat line, okay? So basically, this area is just 2t, and then we are basically evaluating from 1 to x. So basically, we are looking at 1 to x.
So take the antiderivative?
Take the antiderivative, right.
Oh,
Okay, so this becomes 2 times x minus 1. Yes? Yes? Okay, now take the derivative, which is what we want to do, right? So it's just 2. Yes? Notice what happens. If you, distribute 2x minus 2, and then so what happens is that when you take derivative, the last one always becomes a constant. That's why it's always gone. That's why it doesn't really matter where you start. You just have to make sure it starts at a number. Because when you take derivative, that constant is just 0. So it doesn't matter. Does that answer your question, Jonathan? Because your question was, does it matter if we start at 0 or 1, or does it matter where we start? The answer is no, as long as it's a constant. Because when you take derivative, that always goes away. Okay, questions? No questions? All right, let's see. What should we do today? Okay, let's do 2 more questions where it's a little bit harder, but I think you guys can do it. Let's look at this question. d dx of integral from 1 to x to the 4th secant t dt. All right, so copy down this question first. We want the derivative of this integral. All right. We know that the derivative of this integral is just that function itself with x. However, notice the limit. Is the bottom limit a constant?
Yes.
Yes. Okay, so that's good. Is the top limit a variable by itself? No, so then we cannot just say that it is secant x. Okay, so that doesn't work. The derivative now becomes secant x to the 4th because we just substitute in. However, that variable, because it is not an x, we have to do a chain rule. So we have to multiply by the derivative of this thing. So this becomes secant x to the fourth times 4x cubed. Okay, so let's kind of do it this way. So d dx of 1 to x to the fourth secant t dt. So instead of x to the fourth, let's just change it so that it is, we're going to use substitution. Let's change it to u. So this becomes 1 to u. Secant t dt doesn't change, but we are taking the derivative of d du. So I am changing the limit so that it's now a nice variable, which I want. But remember, my final answer has to be x d dx, not u. So I have to multiply by du over dx. Okay, because at the very end, I have to have a dx, not a du. Okay, so this becomes d du. So this part we know is just secant u. Du dx, well, u is just x to the fourth. So du dx is just 4x cubed, and we're just going to substitute that back in. So secant x to the fourth, and then times 4x cubed. Make sense? Okay, so again, if the limit, the upper limit is not a x or a t or a u or just a variable, if it has anything else, you have to do a chain rule.
So we leave the outside, don't we do the outside for secant?
Oh no, you are not taking derivative of the function. You're not taking derivative of this function. You are just substituting the upper limit in and taking the derivative of the upper limit. Okay, so yeah, that's a common mistake too, just thinking like, oh, I gotta take derivative of that function. No, not the function, but the limit. Okay, let's have you practice. Where is that second one? Okay, try this one. Okay, d dx. If you want to help yourself memorize this a little better, so derivative of the integral, if you kind of think of it, it just cancels. So then this just becomes the variable inside. Okay, so this becomes square root of x squared over square root of x to the fourth plus 1 times, because this is the limit is not just an x, we had to take derivative. So it's 1/2 x to the negative 1/2. All right, simplifying this whole thing, x over x squared plus 1 times 1 over 2 square root x. So simplifying that a little bit more, so square root x over 2 times x squared plus 1. Okay. All right, so let's review what we learned today. We learned FTC Part 1. Part 1 says 2 things. Number 1, g of x is the integral of between 0 and x of f of t dt. So g of x is the area underneath the curve f of x. Because of that, it is a function of x. X is somewhere on the x-axis. So that's part 1, part 1. Part 2 is, if that is true, then g prime of x, the derivative, is f of x. Notice the variable change. It is not f of t, it is f of x. So we change the limit into the actual function. Okay, so this is FTC part 1.